Okay, great. Today I'm going to discuss discuss a project I did with some people from IonQ and QC there, where we ran a machine learning algorithm on a quantum computer. And before I delve into the technical details, since this is, a more general conference than just like a technical one, I want to discuss a little bit about my background as well. So I got fascinated with physics at a pretty early age. It was actually through this book that I read called A Brief History of Time by Stephen Hawking. I think I read that when I was 16 years old. I really decided that I had to be a physicist. So I went to the Indian Institute of Technology in Delhi to get an undergraduate degree in physics. After that, I was fortunate enough, after 4 years there, I was fortunate enough to get accepted to this place that looks like Hogwarts over here. So basically Princeton University in New Jersey. And over there, I got a PhD in condensed matter physics. So it actually was not even in quantum computing. It was in condensed matter physics. At the end of my PhD, at that time, actually, the quantum computing world was not what it is today. There were not so many companies and startups popping up that were doing quantum computing in industry. It was mostly still, this was in 2014, it was mostly still a pretty academic field. And, at the end of my PhD, I looked at, I talked to a lot of postdocs who said that it was really hard to get a full-time tenure track job in physics. So I didn't want to spend like a long time of my life doing postdocs. So I decided that, okay, fine, let me just try out industry for a while. And so I got a job as a software engineer at Intel Corporation in Oregon. And so here on the left here is a photo of the Intel research facilities in Oregon, and it was actually quite fascinating. When I first went there, it was the largest building I'd ever seen, and all of it was like basically one giant fab. So I went there as a software engineer, and then I worked my first year at Intel. I worked on computer vision stuff. But very quickly, like about 6 months into that, I realized that I actually did enjoy being a physicist. And then coincidentally at the time, they had just started their quantum computing research group, and I applied to that job and I transferred. At that time, and that's when I actually entered properly into quantum computing. And so I spent a total of 5 years at Intel. I mostly focused on near-term applications of quantum computers. So, starting with 2-qubit systems at the University of Delft, going on to 5 and 7 qubits at the University of Maryland in Chris Monroe's lab. We demonstrated a series of small algorithms running on these near-term quantum computers. And then just last year, actually, Chris Monroe, he asked me to join the company that he had co-founded, IonQ. And of course, I said yes, because I was very excited by their technology. And so here I am. So I'm a senior applications researcher at IonQ. Now, IonQ is based in Maryland, but I just work remotely from Portland. And I guess that's with the way the pandemic is going. I guess that's going to be how it is for a while. I'm going to since that was the intro slide, I'm just going to stop sharing for like a minute and see if there are any questions. No questions? Okay. So let me go back to the PowerPoint. Okay, So let's start with the technical part of the talk. Many of you might have heard about quantum machine learning. It's one of the most, quantum computing nowadays is a field with a lot of hype. And then QML is one of the subfields in that field that has even more hype. But to begin with, I would like to sort of ground ourselves in saying that while machine learning is a very attractive area for quantum computers due to the wide range of applications of actually classical machine learning, the reality is that the algorithms that we know with a provable speedup only seem to work on long-term fault-tolerant machines because they require a large number of qubits. And also they require many, many gates. So they don't really fit in with the model of algorithms that we know work for, that seem feasible for near-term quantum computers that may have limited or no error correction. And on the other hand, near-term algorithms, which basically involve designing some kind of variational circuit, rarely have proofs of their speed up. And since we don't have very large quantum computers yet, they cannot be really tested at scale. And so in this work, what we're going to do is bring quantum machine learning closer to reality by overcoming a critical, what was so far a critical roadblock in the field, which is loading classical data into a quantum state. Here I'm going to borrow some slides from my co-author Jordanis, and talk about one of the applications of machine learning, which is classification. And then in classification, it's a very widely used application. So, for instance, everybody probably knows, has encountered software which can classify dogs versus cats. Also, we have, you can think of applications where you want to classify different species of let's say a flower, or character recognition, which manages to recognize the different digits between 0 to 9, or applications in the medical field where you try to automatically detect whether, let's say, a scan of a brain has a tumor or not. Let's say we want to design a quantum algorithm for classification. I'm going to give a very general overview of how we would go about that. The first step would be to pick an algorithm, and in this work, what we picked was the nearest centroid classifier, which is one of the simplest algorithms. So the steps in this algorithm are first basically construct a model that fits the data. So let's say you have a data set, as an example, the one given on the right over here. So in this data set, to fit the model, all you do is find the centroids of each class of training data. And the second step in any machine learning application is to predict the labels of new data. And for this, you calculate, so if you're given a new point, you calculate the distance of this new point to the centroids of each class, and then assign the label of the nearest centroid. You can do this, of course, very easily on a classical computer. And the way we map this algorithm onto a quantum computer is to compute the distance to the centroids. So to make the part where we compute the distance to the centroids, we do that on a quantum computer instead of the classical computer. Once we've decided what the quantum algorithm is, the second step is to design the quantum circuit. And in this case, Jordanis from QCVer, he designed this distance estimator circuit. So given if you were given two data points, let's say the new point over here and the centroid over here, you can compute the distance between the data points X and Y on the quantum computer. And the circuit that was designed had some very nice properties. First of all, it was very shallow. So it was only log depth in the number of features in the data point. It turned out that these circuits were actually extremely robust to noise as well. Once the algorithm was designed by QCware, that's where IonQ came in. We decided to test that quantum nearest centroid algorithm out on an 11-qubit trapped ion quantum computer. We used gates that were native to the IonQ machine, and tested 4 and 8 qubits, which had 12 and 32 qubit gates respectively. And so, if people are not too familiar with the details of the state of the art of quantum circuits, really is running 32 qubit gates on an 8 qubit running 32 qubit gates on 8 qubits is really pushing it in terms of what the hardware is capable of right now. Now, when we test an algorithm on a near-term quantum computer, one of the first things you have to do is look for what the noise will do to the output. And therefore, even before implementing it, we went in and did some analysis of what would happen. And so basically, what we realized was that on an ideal quantum computer, the output state has a very nice form that looks like this. But on a real quantum computer, the output will have finite probability even outside of these of what is called the unary encoding basis. So you can see it visually here. The output of the real quantum computer looks like this figure on the left. What we did to address the noise was we designed an error mitigation technique, which post-processed the probability distribution output from the quantum computer to discard states that were not in our encoding basis. And we got this very nice and clean probability distribution afterwards. And this proved, even though this was a very simple method, this proved critical in obtaining accurate results from the implemented algorithm. So I'll very quickly go over the results since we're close to the end of the talk. But basically, here are the results for some synthetic data, and the blue shows the raw data, and the red shows the data after post-processing. And you can see that after post-processing, the classification error for over here, NQ denotes the number of qubits, was significantly reduced. Over here, we see results for classifying the iris data sets, which is basically 3 different species of an iris flower. And you can see before and after error mitigation, the results improved by quite a bit. We went on also for the first time to classify all 10 digits of what is known as the MNIST dataset, and we obtained accuracies that were extremely comparable to the accuracies of a classical nearest centroid algorithm. So to conclude, we ran the quantum nearest centroid algorithm successfully on real-world data sets with up to 10 classes on the IonQ systems. During this, while running this, we got a crucial insight that using sparse encoding allows for effective error mitigation techniques by loading data into classical data into quantum computers. We're excited about what we can do with IonQ's newest 32-qubit system. Okay, so I tried to go quickly over it, and I will open it up to questions. Are there any comments? Okay, oh, here we go. There are comments on the right. Oh, there's a lot of them. Okay, hi, hello everyone. There's a lot of people saying hi. So one person says how to design circuits, asks how to design circuits based on the algorithm. So basically, that's both a science and an art, I would say. once you have the algorithm in mind, coming up with the first version of the circuit is pretty straightforward. But then what quantum programmers basically do is optimize do a lot of optimization to get the best possible implementation with the fewest possible gates. Possible gates so that you can get the best possible accuracy when you run the algorithm on your quantum computer. And then somebody asks, do you have a Hamiltonian for your MLQ system? I'm assuming that says machine learning quantum system. So of course, there's my cat in the back, but the physical qubits themselves, they're ions and they have a Hamiltonian, but we don't use a Hamiltonian formulation to design the algorithm in this case. So somebody asks, what's the archive link? Let me just put that in the chat myself. Okay, here we go. Here's the archive link. I put it in the chat. Someone asks, I would enjoy if you walked us through the quantum logic of your circuit. So I think that would require more than a couple of minutes, but it's really well explained in the archive link. Please look at it there. And then if you have questions, please email me or get in touch with me, and I'm happy to explain more. Someone asks, is this similar to the K nearest neighbor algorithm in classical ML? Yes. So in fact, most of the steps, so the K nearest neighbor algorithm in classical ML actually uses a nearest centroid procedure as part of that algorithm. Here we use a quantum nearest centroid. Here we basically quantize that nearest centroid procedure. So in that sense, you can combine this quantum nearest centroid algorithm. You can incorporate it into the nearest neighbor algorithm in classical ML. Yes. And then what were the advantages over classical methods? So again, that's basically, there's a good discussion of that in the paper. I think there's Denise telling me that it's my time.
Thank you, Sonika. That was amazing.
I mean, sorry, I kind of had to go fast because I was not used to it, but that's fine.
I think you did a great job. It's a great paper, so I suggest everybody to read it on archive, and maybe if you want to have a further discussion with Sonika, we can schedule a time for a group of you. Since Sonika is really overbooked, not a complaint, but it's just a tribute to her skills. What I want to do is say thank you, Sonika, and get everybody to move on to our next talk.